Okay, so welcome all. This is 10th session for the data structures algorithm in Java. So in this session, we are going to talk about the sorting algorithms, why they are important, and we are going to see the implementation of them in the Java. And we will discuss the most of the good aspects of or the bad aspects of the algorithms. So let's start with it. So I just let me share the screen. So I think just started. Just let me see. Started or not? Yeah, I think it's. I think we can start. Okay. So basically, sorting algorithms. We know it's one of the searching and sorting. They are the one of the most simple and at the same time more crucial type of algorithms that are quite much needed in our places because everything we do requires some kind of search and some kind of sorting, be it Google search or be it in your database. If we want to retrieve some data and we want to filter them, you have to sort them. But at the same time, there are so many algorithms are there, which one to choose. There's no best algorithm per se. At the same time, uh, everyone specified the needs according to their own. So at one time, like for example, today we might discuss the four sorting algorithm here based on our time: bubble sort, selection sort, insertion sort, merge sort, and all. In that, there's a lot of factors which come into the picture, and how it varies from different places to places. That is something we are going to see in this. So we were going to discuss mostly the four sorting functions here, and on top of it, we're going to see what kind of sorting we can categorize this algorithm into, and how they perform in this situation. And we have to see from mostly from the real perspective here, where the database and the where you have a lot of data. And if you when I'm saying a lot of data, it might be 10,000 records, lakh record, crores of records, and all that. So how they are doing it? So for example, we are using Instagram and Facebook or any social media. They might be sorting over certain preferences. They put advertisement in between. How they are doing that? Some logic will be there. So those are still at when we actually look about, they are much more at the higher complex level. But for now, we should start looking from the basic, from the scratch, how it can be done. And because from this only it is going to build up, and more different data structures can be used to sort the stuff, to sort the record. Right now, the sorting algorithm that we're going to see is mostly based on arrays. Only array manipulation will be happening here, but as we go more complex in detail, the data structures vary drastically. So a data record might be a table, or data record might be a NoSQL kind of stuff where the data is not at all structured. So how do we sort them? So all this thing come into picture. So before coming to implementations of this sorting class of algorithms, we have to see the type of. So we generally consider two type of aspects in sorting. What is one type of sorting, and then another is sort stability. So let's start with type of sorting here. So one is something called internal that one type of is called internal type of sorting, where the elements that we are going to use in the array, uh, and they are going to arrange themselves in a particular order within the array without using the extra memory. So if we are having when we say internal sort, that means it will use the in memory, the terminology called in memory placement will be happening within the array. So if we have element of 10 array of 10 elements, they will be swapping within the array to get it sorted. So that is one, and most of the basic sortings are actually is involves in memory placements. But at the same time, apart from quick sort, most of them are little expensive in computation. Okay, so apart from quicksort, we can discuss quicksort at a later point of time, but they are quite little expensive in nature. Now come down to external sort. External sort, what type of sorting? What is happening is we use external memory, extra space. We use extra space, which will take it as a auxiliary space, which we're going to use it to keep the in between data. That when we are processing, we might have different stages, right? So at those different stages, we use these extra spaces to keep our intermediate results, and once everything is sorted, we kept that keep down to main memory. So uses of extra space quite uh, is quite beneficial. It is less in computation. Most of the people consider that computational wise it is less expensive, but at the same time, memory wise it's quite expensive. Means if you're talking about 10 element, it doesn't very much matter. But if you're talking 1 lakh record and you're using certain algorithms like merge sort, where you have to divide an array into different parts and then different parts, so there are a lot of intermediate stages are there. So that means we need more data, and we are not talking data that if we have one array, so we might have 2x. Sometimes based on the sortings, we might get something 3x or 4x usage of memory might also happen. So which sometimes is not at all feasible if we dealing with large sort of data. So these are two aspects, internal sorting and external sorting, which mostly related with the memory aspect. Whether you use the given memory and you try to sort the elements in a particular order, or you use external memory to store intermediate results and then put everything together and give the final result. Now, another one is sorting stability. Okay, so what does it means is, for example, like I have an array. Now this we can call it as this. Okay, now if I want to make it ascending, I will just write it as 4 7 6 8 8 9. Now the thing is this, if we are saying it's the algorithm is actually a stable algorithm, that means this 8, the first position 8 in the sorted array, and this position which is kept at the 4 in the original array should be same. They should not swap. So the position of the so the position of the particular element, if even though they are duplicated in a particular array, they should keep their position first. That means this 8, the highlighted one, should come before the second 8 which is at the last of the input array. So they should maintain that order, and this is quite much useful in the database sense, where uh, a row can be duplicated, a particular element can be duplicated, but they are kept in a specific order for the certain purpose, and they should respect that thing. So for that, sort stability is actually gives us confidence that even if they have a duplicate element, they will preserve the order. So in short, they should preserve the order. Basically, they preserve the order of the elements, and the unstable would be which doesn't preserve the order of the element. So I can say that this 8 in the input array can be put in front of this the first 8. Okay, so the order might differ, and in it depends application to application. Sometimes quite crucial, sometimes it's not crucial. We have to see the based on the use cases that we are having. So unstable is basically doesn't preserve the order of the elements of duplicate elements. Duplicate elements would be better. Okay. Okay, so these are the two terminologies that we have discussed. Type of sorting, that is internal sorting, external sorting, mostly in terms of the memory aspect, and the sort stability, that means the position of an element, or specifically a duplicate elements in a particular array, or in terms of in a general record or element, whatever we try to resolve. Okay, now the thing is we have to just a minute. So now what we're going to do is Based on this, we have to keep this in mind, and we will again come back to this a little bit more in between, uh, and we will discuss the type of sorting that we are using, whether they actually come down to these categories or not. For example, in internal type of sorting, all the basic sorts, that is bubble sort, selection sort, quick sort, they use internal type sorting, that they don't use any extra auxiliary space, memory space, whereas merge sort actually uses it. Okay, but at the same time, merge sort, insertion sort, bubble sort, it's actually quite stable, they preserve the order of the element, but quick sort doesn't do that. But that doesn't mean, so we can argue that okay, bubble sort, insertion sort are quite good in this aspect. But if we want to bring another dimension here, we can look at the time complexity. So usually the sorting arrays will be in the order of n to power 2. I'll just put some, okay, I don't have that symbol. Okay, so it might be n to power 2 or n log n. These are the, generally in most of the famous sorting algorithms you will find this kind of time complexity. So n log n can be achieved by merge sort and quick sort, and the n square mostly developed by the bubble, insertion and all. So there's no perfect algorithm which can have all the stuff into the picture. They might be, but again some constraints would be there, that how the data should be, how what is the nature of the settings that they are working upon. So multiple dimension we have to consider while selecting a particular sorting algorithm for your particular application. Okay, that being said, let's start with the, to just given this background, let's start the implementation. So what we are going to do here is, I will just tell you the basic of the algorithm, how this work, and then I have written the most of the code here as a basic template, and then we're going to write the actual logic of the selection of particular sorting, because writing everything else might take time. So I will just give you the first template wise. This template is going to follow in the all the other all the sorting function that we're going to see today. So we will start with the main function, where we are going to create an object, and we will have a predefined array with it, which will be unsorted, and we will pass this array as one of the input, and and whatever the name of the function will be, in this case sort, we will pass it, and this sort function will be the core logic here. In this core logic we're going to discuss and write the core logic, and then in the void print array we'll print the sorted array. So that's the template that we are going to use in all the settings. Okay, now coming back to the selection sort, this is the first type of sort that we are going to see. It is called as the simplest sorting algorithm, that is the basic one that you can use, and we might knowingly or unknowingly use it when we try to sort certain things in our place. So what does it define? So what it says is, selection sort is, you first find the smallest element from the array and put that at the its appropriate position. Okay, then you first, since you find the smallest one, then that is sorted, then you take the remaining n minus 1 array, and then from that you find again the smallest element from that, and then you put that in the sorted array. So if we have to say, let's take a basket, so there will be a sort basket and there is an unsorted basket. Initially array will be unsorted. So at every pass, there's something called pass. Okay, that we pass or iteration. So at every cycle of pass, a certain element will be kept from, will taken from, element will be taken from unsorted part, which will be minimum in this case, in the for this particular algorithm, minimum value element, and we will put this in sort basket. Okay, so that's how it will work. So for example, right now we have an array which starts with 12, 29, 25, 8, 32, 17, 40. In this is an unsorted array. In that we have found that 8 is the smallest one. So what it is going to do is, it will take out the 8, it will take out and it will put in the front. So in the second line, if you can see, this will part will become 8 will become the sorted because the minimum element that we have found, and then the rest of the element will be swapped. So what we are doing is, once we find the smallest element, we'll swap the value from 8 to 12. We're just swapping the exchanging the space, but the basket of 8 will be kept as it is. Now the next remaining unsorted value will come in the left hand side. Now again this is the first pass, you can say. This is the first iteration of the logic. In the second iteration logic, again we have to find the smallest element value from this unsorted array, and then we have to take that and put that in the basket of the sorted array. So here we found that 12 is the smallest one among that, so we will swap that 12 with 29, because from here, because this is unsorted and we have to start with the unsorted part and then find a minimum element and swap the places. So once we are doing that, again the basket will increase over sorted and we'll find 8, 12 as a sorted, and the rest of the 25, 29, 32, 17, 14, they will be in the unsorted part. So like that, the unsorted basket will be emptied and sorted one will be increased as it going. So we are mostly doing the ascending order, that means smallest element first, the top element with the last. So that's a general basic thing. Whenever you take a sorting algorithm, so we consider that ascending will by default. So let's start writing the core logic for that. Okay. So here given in the from the main function, we'll pass some array value and then we're going to pass it as a value in the sort function, which where we'll write the core logic. And then here we will first we have to identify the length of the array. So for an array in the Java, you can, if you directly write arr dot length, you will get the size of an array. So once you find the size of an array, then you can start, you will get an idea of how the length of it, and then you can start analyzing the particular array. So we will write a for loop function in this. So it will be I minus 1. Okay, so we'll, for the first loop, the outer loop will be, okay, the outer loop will basically go one by one step. So it will start at 12. So the first outer loop will go at, will only check it will move ahead on the left hand, sorry, at the right hand side one by one. So for that we are taking the outer loop. Then here we are going to define that the first element would be, so here instead of element, we are mostly discussing with the position value, because we have to just swap the values here. So we will take the minimum as minimum, the value min as the position value. So we consider that whatever the I value will be, it is a minimum value, and then we check the rest of the array to see whether we can get a minimum value less than the min position or not. If we get it, let's swap the places. That's how it will work. So in that, then we will write the another array in this, where it will start with I plus 1. That means it will start looking for the element from this original thing, from the initial, from the, okay, from, it will start looking for the rest of the array from here, and it will go till n, and it will go for j plus plus. In this, we are going to check only one thing, that is, what is the value, the rest of the value we have, that is, we are looking from the j loop, whether it will be less than arr of min or not. That arr min is basically the position that we are having here. So if it is there, that means in this, we kept minimum position value as 12 initially. Now we are checking from the rest of the element that is there any position whose value is actually less than the first position, that is 12. So it will check for that. So once it checks for that, if it finds it, so we'll just assign that position value as min equal to j. Now what we are going to do is, once we find the minimum position value, that there is a value at particular position min, which is lesser than the original assigned value. So what we are going to do, we swap the element out of it. So for that we are going to use the min function, and in the min we'll keep the value of I, and arr min we are going to ARI will keep the temp. Okay, so that's how the logic will goes here. Okay, so again this outer loop to move one position ahead in the array, this is for that. So moving the element, and in the second loop basically we are using it to find the minimum value from the rest of the array. Okay, so this is a core logic, this is a basic logic that we can find it out here. And okay, let's run it. Okay, so for an array of 64, 25, 12, 11, 22 and 11, it is giving us the value 11, 12, 22, 25, 64. That means it works perfectly fine. So this is the basic array that we can think about for as far as right now. Okay, so here the only again to summarize in one line, it will find the minimum value from the rest of the array and will put at its appropriate position in the beginning. Okay, this is the basic selection sort. Now let's go with the bubble sort. So in bubble sort, okay, so bubble sort is like it's a opposite version, or you can say, of the selection sort. Here in the selection sort we try to find the minimum element and we keeping them in the front. Here this thing would differ. Here we try to find the largest element by comparing the two adjacent element, and then we keep them at the last. Okay, so for example, so we have an array of 13, 32, 26, 35 and 10. That is the original. Then we'll compare the two adjacent elements. That means 13, 32. Then we will see, we will first start comparing 13, 32. We found that okay, they are at 13 is less than 32, so we don't need to swap. Then what we'll do is we will compare between 32 and 26. We found that 26 is less than 32, so we will swap it here. Then we will find that 32, 35. So when we start comparing 32, 35, we found that they are still in a perfect position because 35 is bigger than 32. Then we will find that 31. So then we'll find comparison between 35 and 10. We found that 35 is greater than 10, so we will swap it. So in the first pass, after the first pass, the value would be, this is the condition of the after first pass. Okay, now in the second pass same thing again will happen. We'll go till the nth pass where we'll get a sorted array. So now again we will see that 13, 16 will compare. We found that okay, they are perfectly normal. 26, 32 we found that it's perfectly correct because 26 is less than 32. Then we'll find that 32 and 10, when we compare them we will find that 10 is less than 32. So we will do that. We'll swap these numbers and then we'll find the 35. So if you observe here, the largest elements are getting sorted here, and the smallest element we still have to sort. Okay, so this is it's a different it's a little opposite version of the selection sort. Similarly, if you go down, we'll find the sorting element. So that's the basic logic of the bubble sort. So now we have to implement them. Basically we will see that again the system is template is same. We will have a main function, we'll have some predefined array, then we will have this we'll print the array as a print array function. In the bubble sort, what we are going to do, that means we have to write a logic in a such a way that we find the largest element and we start keeping them in the end. So for that, again the basic outline will be, the first we have to identify the length of an array. to perform computation from through the loops. Okay, then we are going to write for int equal to I equal to 0, I is less than n minus 1, because uh, this is a lot, because we have to go only n minus 1 step, because we are comparing between two numbers, so only n minus 1 passes are more than enough for us. So this one is basic, this outer loop is basically for comparison between two numbers. Okay, sorry, the outer is basically to see the outer loop is only uh, for the passes, the number of passes till we get the proper sorted pass. That is, now if in the inner loop, this loop will be basically for comparison. So what we are going to write is j is less than minus I minus 1. Okay, I will explain this why we have write. Okay, so in the jth loop we are starting at 0, but what we are doing is n minus 1, n minus I minus 1. Why we are doing that, we will discuss like right now. So let me just write the code. So this loop will be used for comparison. Loop for comparison. So uh, so we just have to see that whether AR of j is less than or greater than, mostly greater than AR of j plus 1. That means we are saying that whether the earlier element is greater than or not. If it is greater, you just swap it. ARij and int ARij plus 1. In j you will just value of ARij plus 1. So here we are just changing the value of adjacent values. We are not swapping just like selection sort where actually the different position value will be swapped. We are just comparing two adjacent values, and we are just changing them. Okay, I think yeah, that's it. I think this is the only thing that we need to write, and let's remove this. Okay. So what is happening here, if we had seen this here, at the first original cycle, it is like 13, 30, 32, 26, 35, 10. After first pass, we find that 35 is fixed in this position. In the second pass, 32 is fixed in the position. That means the only our scope area of focus should be limited to this, the unsorted part. So that's why from the distance, from the back of the array, we are decreasing the value one by one. Based on the I value, because we know that the larger elements are getting sorted automatically, so we don't have to look at them again. So that's the beauty of one of the bubble sort, that it's not going and repeatedly checking again and again for the sorted part. It knows that okay, this part is already sorted, I don't have to see it, so I will just focus on the unsorted part. So it is trying to reduce the repetitiveness that is actually happening in the particular algorithm. Okay, so just let's run this thing. Let's see how it will run. I think okay. Let me see whether it's running or not. Okay, why it's not running? The console is not coming. Okay, let me check console. Yeah. Okay. So yeah, so given an array of 64, 34, 25, 12, 22, 11 and 90, here we have seen that 90 is fixed, so at first iteration it will be like this, but the focus will be remaining on the rest of the array. That's 64, 34, 25, 12, 22, 11. So based on that, it is showing correct. But how do you analyze it, that whether it is good in the last setting or not? So you have to sometimes keep on experimenting with stuff, mostly not on the function in this, but mostly on the pen and paper. Why? Because they are very fast. They will give you the answer in a milliseconds. But we have to see, suppose if I give an array just like this, which is already sorted. So how much time will it actually take? We have to ask this question sometime. The reason is very simple, that it, if it's already sorted like this, for example, I have given a sorted array, and this is small array, so we might not actually understand the value, but let's take 100 or lakhs of records. In that, if the record is already sorted and again you try to sort in the same way, is your algorithm is going to take the time or not? Is it going to check each and every element, or is it going to understand that okay, it's already sorted, I don't have to do? So is there any way for do that? How we can identify it? So these are the questions that you have to keep on asking while developing a sorting algorithm, even while using the sorting algorithm. uh, so for example, bubble sort, if here we are just looking at, we are, what we are doing is, at from j to j minus 1, we are again comparing j to j plus 1. Like that means, from apart from the sorted one, we are checking again and again. That means irrespective of, even though it is sorted, we are still checking the rest of the elements as well, which is quite good. But if we can add certain kind of stopper or mechanism which tells us that okay, it's already sorted, that would be great. And they are mechanism, and they are little more complex, not exactly complex, but they are there, which actually let us define that if given an element which is actually sorted, the program should stop. Okay, so that is one thing that we need to mostly think about while actually uh, writing an algorithm. Okay, so always think about different kind of scenario. You have to experiment with them. Now, what if it is sorted? What if it's not sorted? Or right now we are, what we are doing is, it's ascending order. That's the order we want. But what if we write in a descending order, and how much time will it take? So these are the questions that we have to keep on asking to ourselves. And let's say another aspect, that right now you're doing for numbers, we mostly do sorting for numbers. What about the characters? If you put characters, how are you going to do that? Is there any way to do it more fastly, or you have to compare them? And how are you going to compare them? Okay, can you use ASCII functions? Can you not? Can you use something else? These are the questions that you have to keep on asking while developing a particular sort. Okay, so this is something you should keep on thinking about while doing writing any other program. Also, you have to think of multiple lenses, multiple scenarios, multiple dimensionalities, and first of all, you should also look out for scale. Okay, so till now we have seen two sorting algorithms, and both of the sorting algorithm, that is selection sort and bubble sort, we are using two for loops. That means, by in short, if we have and that too we are taking them to the length. So its time complexity for both the thing will be n square. I think I can't put the 2 at the top, but you just write n square. Same be it for selection sort, be it for bubble sort. But bubble sort actually give us a little bit more faster evaluation when it comes to most of the sorted part. It gives us much more better understanding there, as understanding when it comes to the speed. So bubble sort is one of the basic, at the same time still preferable sort when it comes to actual implementation. Okay, now let's move on to the third sorting function, that is called insertion sort. Okay, so insertion sort is something also can be related from the real life. Like if you have played the cards, obviously you will get the cards in an unsorted way, and you have to sort them. So how you usually sort them? So based on that idea, it all comes down to the uh, idea of insertion sort. So let's discuss about how it actually do. So we have first this initial array, that is 12, 31, 25, 8, 32, 70. So what it will do is, it will start comparing first between two numbers. That is, first is 12, 31. Okay, it is perfectly fine. 12 is less than 31. 31, 31, 25. We found that okay, 25 is less than 31. So let's swap it. So when we are swapping it, so it will become 12, 25, 31. Now, is it going to stop? No. What it's going to do is again it will check after coming here. It will again check that whether 12 is greater than less than 25 or not. That also an evaluation will happen. Okay. So what it's doing after swapping, it is keep on checking the back that whether they are sorted or not. Okay. So now in this case, everything is fine. 12 is less than 25, 25 is less than 31. Now when 31 compare with the 8, we found that 8 is less than 31. So what it will actually do, it will it will swap with 31, but it will end no. What it will do is it will try to arrange this one as well. So once it swap, it will again go back to its older part of the sort, which they assume that it might be sorted, which might not, might not be true. So it will check that whether 8 is bigger than less than 25 or not. If since it's not, so it will swap. So so 8 will come here. Then it will compare 8 with 12. So it will come here. So 8, 12, 25, 31, 32, 70. Now once it's done, it is still is mostly in the sorted part. So that means we are checking that the moment we are swapping and we are moving forward, we are also keeping the back side as sorted. We are not keeping them till the last moment that it will automatically sort. It will, what is happening that okay, till 31 let me see that whether I have everything sorted or not, then I will move out to new elements. So from 31 again we'll check 31, 32, they are quite sorted, not an issue. Then we'll check 32 to 37 and 32 to 17. We found that 17 is less, so it will do the swap. So we will just write it down. So it will become 17 and 32. Then again it will check 17. Since we have swapped, now it will check all the elements which are earlier to check whether they are already sorted or not. So it will do 17 and then it will come to 1731. So let me write it down. So it's 1731. Then again it will check 1715. So it will swap here. Again it will check 17 and 12. It is perfectly fine. Then we'll check 12 and 8. So that's how it will, somehow it will arrange, based on the logic it will arrange themselves as sorted. So how it is different from insert bubble sort or selection sort, there we are trying to assign one value at a time. So either you find the minimum value and then you put it the first, or you find the maximum value and put it the last. That's how the selection sort bubble sort was working. But here I am swapping between the numbers, and once I swap again I will check the back part of it to check that whether they are sorted or not. If they are not sorted, sort them again and then move to next element. So that's the in a nutshell, that's how the insertion sort work. So again, to implement it, we will try to find the array of the length of that array. Then for we'll write the outer loop, which will again move the element from left to right. And plus plus I. Then will take a key. Okay, the key will be here, the key will be basically the first element, for example 12. Okay, and then what we are going to do is, and from that key we will try to find j is equal to I minus 1. Okay, so what does it, we'll explain the why j is equal to I plus 1, but we will go to that. Let me complete this thing, 0 and then ar j whether is less than key. If they are less than key, I will swap this thing out, and ar j and j I will reduce to minus 1. And just I will write ar j plus 1. equal to key. Okay, so let me retrieve back to what is happening here. So what we will do is, every loop we will start with assigning the key. Usually the key would be like this. So we will take the 12 as one of the thing. Like for example, at the first pass, it will be the, sorry, we will start with 31 because 12 is the minimum, right? So we have to take. So here the first thing will be 31 at the first pass, and j will be at the value of 0. Now it is checking whether j is less than 0 and AR of j is 0 and less than key or not. Since this is not satisfied, this condition will become false and it will move to second time, that is I plus plus. Now the key would be 25, and then it will check whether j is okay. I did one mistake. I'm reducing, right? Okay, yeah. Okay, so in the first iteration, the key will be 31. It will, and the j value is 0. If j is greater than or equal to 0 and AR of j, that is AR of 0, in this case it is 12 and key is 31. So once the key is there, if it is less than that, sorry, if it should be greater. Okay, yeah. If it is greater than the key, we have to swap the elements between them. If it's not greater, that's totally fine. We will move to we will move to the next element. That's how it will be. So now 31 is done, then we'll go to 25 and j value become 1 because it is always take this, and then it will check whether from 25, that is from 25, it will check its all the previous values to check whether they are sorted or not. If they are not sorted, swap them. If they are sorted, move on to next loop. Then it will go to, then it will change and it will go to the 8, and from 8, and it will look out for 2. That means it will run for 3 times. So from 8 as a key, it will run for all these 3 elements to check that whether they are in a sorted position or not. If they are not sorted, because they will check whether the jth value of particular array is less than key or not. If it is less than key, it's totally fine. But it's greater than key, it will have to swap. Okay, so that's, in a nutshell, that's how it will, we can write it down for uh, for the insertion shot. Okay, so this is for the comparison part, where you're looking at one element, and from that all the previous element will be sorted accordingly. Okay, so this is how, and then whenever you are swapping the numbers, you have, at the final, you have to, wherever you're swapping, you just assign the largest value into that particular position. So that's how it will be. Okay, now let's run this again. It will also should give the sorted value. Okay, so given a 11, 12, 11, 13, 5 and 6, it is giving us 5, 6, 11, 12, 30. So it is working perfectly fine. But again, you have to see mostly the idea of for how they are actually writing the algorithm, by taking the inspiration from how we actually sort, by naturally or by using certain our own logic. Okay, here we are not trying to place element just like that. We are actually checking, okay, let's take one element, from that we see that whether the earlier elements are sorted or not. This is the main idea of the insertion short. Okay, now the last part of the sorting algorithm we're going to see today is the basically a merge sort. Now it's come down to, merge sort is one of called divide and conquer technique. So if I have to say divide and conquer, in this course, unfortunately, we don't have this kind of techniques, because there's something called as divide and conquer, greedy algorithms, different kind of techniques are available, and these techniques are quite a kind of base to write to, which are base for writing all the different kind of algorithms that existed right now in the in particular algorithm space. So divide and conquer is one of them. So it just tell, in a nutshell, it tells that I have a problem P, I will divide them into, let's say 2 half. Then these two halves again will be divided into another two halves. So just like that it will go down till it reaches to a one where a problem will be the problem will be divided till it cannot further divisible, and then it will try to solve the particular problem, and the same problem how we are solving for the smallest unit, we are going to apply that for the larger unit as well. So that's a divide and conquer. So you divide the problem into multiple parts till you reach to a lowest point of the problem, and then you try to solve that problem. The way you're solving the problem should be same for the other problems as well as you go upper and upper. Okay, so to give a nutshell of mud sort how it works, what it will do is it divide this array, for example this is array, into two half. So it will divide the array into two half. Okay, this is the left hand side, this is the right hand side. Now after this it will take this as one of the problems, and again is going to divide this problem into two halves. Now again what it is going to do, it still can be divisible, we found that it can still be divisible. So again it will try to do for 14 and 33 as well, till the time you can't divide 14 more, you can't divide 30 more here. So this is the smallest part single unit. Now from this single unit they try to see whether, then they try to compare this element together, that is 14 and 30, they will compare and they will see whether they are sorted or not. In this case they are sorted. Now let's take an example for 27 32. So once they go to a stage where they cannot be furthermore divisible, this 27 and 10, so they found that okay 27 is bigger than 10, so what it will do, it will combine and it sort this thing, that is 10 and 27. Similarly for it 14 30 also it will, now it will try to merge it. Okay, so once you divide the problem you have to conquer also, you have to conquer the particular original problem space, right? So you have to merge them also. Once you divide you have to solve in a certain way that you have to merge them. So now these two problems, that is 10 27, they are in sorting order, and 14 30 they are also in sorting order. Now we have to merge these two. So then it will come down to, after merging it will be like, so for here it will be like 10 and 27, which is going to be when you try to merge them it will be like 10 14 27 and 33. This is how it's going to merge. Okay, then the same thing you can see for the right hand side as well, till the time you actually sort the whole array. It is considered as one of the faster algorithms, merge sort. It is a very respected algorithm. Many people, many organization and in technical aspect they use this algorithm a lot. But only disadvantage that you can see here if you have to argue against this algorithm is, you see how we are dividing this algorithm into two parts. So we have to keep them somewhere, right? We can't put that in a single array. We have to keep this 14 30 27 10 in a separate array, 35 19 42 as a separate array. After that also when you divide 14 33 as separate array, 27 10 as separate array, just like that we have to keep them. So the memory consumption of this is quite high, it's quite high. But when it comes down to solving the speed, it is one of the quite fastest, because dividing the problem is quite easy, it doesn't take time, the computation is in the order of 1. And merging also, when you're doing it, merging takes max to max log n time. So that's why it's n log n. So you're dividing an n problem of n size into n parts, it will take n time, and when you're trying to merge it, it will become as a log n. When it's merging, it will take log n time. So that's why its time complexity is basically is n log n. Okay, let's try to write the function here. Okay, now let's try to write the function of this. So again the template is same. We have in main function we have defined some array, we are calling the merge sort function. merge sort object. From that object we're calling the sort function, and then we are printing the array. Now before writing a merge, we have to define a certain function. We have to define a certain another template that we have to give, such that we can divide the array into multiple sub problems. So for that, sort function will be used. So it is actually used to divide the problem into sub problem. Now in this, let's give you another more aspect. Here int array is the basically array. L will be the L and R, it is the lowest value and the highest value in terms. Right now in this term it will be the lowest value, and they are the pointers basically. So when we say pointer, that means L will be the, in this case, like when we are dividing an array into two, so it will be the lowest value of the right sub problem, sorry, left sub problem, and R will be the lowest value of the right sub problem. That means the value, whatever the position value of L will be, here it will be 14, here it will be 35. So that's the value, this starting pointer, their starting position pointer of those things will be kept in L and R. So we are checking that if L is less than R, which it shouldn't be, because we considering that the half part or this left side will be always lesser than the right side, right? That's how it goes. So if it is that, then we'll go and try to find the middle element. So minus L divided by 2. So we find the middle element. Or middle position. In this case, it will be the middle position. Okay. Now from here, we again have to divide it. So it's again, well, like I said, divide the problem sub problem, right? So we'll get our left sub problem and right sub problem. So once we get the left sub problem, right sub problem, again we have to divide it till it point that we can't divide it much further. So what we'll say that we will pass the array, we'll pass the L value, and we'll pass the middle element. So for example, for 14, 33, 27, 10, 35, that is the original array for us. In this we found that at this position, maybe at 3, we have to keep a left subarray, and then we have a right subarray. At this point we have to keep this value m as 3. Okay, this is the point where we have to divide. So that's what we are passing, because for the left subarray, the lowest value will be the L and the highest value will be the m. Similarly for the right, this is for left side subproblem, and for the right side subproblem we will start with array. We will send the array m plus 1 and R. So we are calling them recursively, basically to divide the problem into multiple subproblems. Okay, once we divide this, then we have to, once we divide this, and we have to divide to its core functionality, because it's recursive, it's again call and call it after, because first it will divide the left side of the problem, then will divide the right side of the problem, then we should call the merge function, which is the main function. So in this we'll put the L, so array L, medium and right. So this is what 3 values that we have to store. We have to pass it as a value. Now this is the basic, that's how we are going to call the merge function. That means we are going to divide an array into multiple subproblems, and then once down to the basic unit of problem, we try to merge it. That's how we do. So here the merging process will come into picture, that is merging the solutions. Merging solution means solution here will be the sorted sub problem, sub elements of sorted sub problem. That means 1433 is a sorted sub problem, 1027 is a sorted sub problem. So that is something we are going to find it here. So for that we are going to store certain values. So instead of using L and R directly, since we are going to have, since we have two sub problems, that is left sub problem, right sub problem, we are going to find the length of those problem, the size of that array, sub problem array. So for that we will write L minus M minus L plus 1. This is for the left, and 2 will be R minus M. So this is size of the array of left subproblem and right subproblem, and then we're going to define some temp array here. Calculating the size of the left and right subproblem. Okay, we have defined some arrays here where we are going to put the sorted arrays. So Li new int n1. So this arrays we are going to define. Sorry, I should. Okay, we are just almost completed with this. This is new int n2. So we are defining a temporary array value where we are going to store the sorted arrays. Okay, and then from the original array, that is that we have, we are going to divide, we are going to copy these values here. So copying the data into subarrays from original array, and what we're going to write here is for int I equal to 0, I less than n1 plus I plus plus. We are doing for right now, we are doing for left subarray here. So Li is will be ARL L plus I, and same thing we are going to do for right subarray as well. So what we are going to do, just copy paste it. This for left subarray. Now this is for right subarray. When we are saying array, it's basically a problem that we are saying in a proper terminologies that we have to use here. J, and this will be M plus 1 plus J. So we are giving us L, we are giving because this is a starting location, and doesn't mean that L will be always 0. It can be 1 or 2 at 5 based on the position of the array, because we are dividing the subproblem in multiple parts, right, that we have seen the earlier. So same here, from the M also might differ here. Okay, now what we have to do is, we have to now once we get these two different values, we have to again sort them. Now once we get two subarrays, and we have to sort them because we are trying to merge it here. So let's again define some values here, and k equal to L. Okay, this will be L will be the starting point. So we are right now we are going to merge subarrays, and then we will write the main logic of combining them. So what we are saying, if I is less than 1 and j is less than the size of second subarray, if this is happening, then we will check that whether L of I is less than R of j. I will just show you with the example also what exactly I am doing here, and then the main array we are going to pass on the value. Okay, this is done, and then we're going to increase the value for I, and we just copy paste it, else ARRK will be increased by RJ, and then we'll get by J plus plus, and every time we are doing this it will be K plus plus. And okay, So what we are, this is the main logic here, that is, and this while loop is one of the main logic. So what is happening here, let's take an example here to better understand. So right now we have this. So as one of the sub problems, that is have intermediary sub problems, we will get this. Left subarray will be 1433 and then right subarray will be 2710. Now we have to combine them. So what we have to do is, so L here, the L will be 1433 and R will be 2710. Now what we are going to do is we are going to compare. That we are going to compare whether 14 will compare 14 with 27 and check that whether 14 is less than 27 or not. Okay, then we similarly when we check 14 with 10 also. So once we are doing this, we will find that okay, first we compare 1427, it is big. Then we will check that again sorry, it should be sorted, right? This will be sorted, my bad. Okay, we will check this, it should be sorted. First of all, the sub problem will be already sorted, so it's an intermediate stage. We will check whether 14 is less than 10 or not. So 10 is less, so we'll come back. We'll put 10 in the ARR k value. Okay, so here the else part has been gone here. Again we are going to check whether 14 is now 14 is less than 27 or not, because 10 is already placed, so we don't have to check the 10, we have to check the other remaining aspect of the R. So we find that okay, 14 is less than 27, so we'll put here. So this, in this case, if part has been increased. Then again we are going to check whether 33 is less than 27. No, 27 is less, so 27 will be there. So else part will be there. Now the only remaining part is 33, so 33 will come. Okay, that's how this comparison is happening. It is once a sub problem sorted array are already sorted, and when you are trying to merge them, we just compare between these two sub arrays and then you try to publish it. Now they will be this, in this case we have both have left subarray, right subarrays of the equal size, but usually it not, in most of the case will not be it like that. So what we have to do is, suppose a right subarray is left subarray is greater than that than right subarray, then we have to, once we have done with the major most of the things, the remaining element we just have to copy that in the array. So what we have to write is, while I is still less than n1, we just have to do ARR k and L of I, and then we'll just increase the value. So what we are doing here is, there will be a situation where a left subarray will be much greater than right subarray, or the right subarray much greater than left subarray. In such cases, once the comparisons are done, the remaining, there will be certain elements might be left in one of those arrays. If those case arises, you just have to copy paste those arrays in the final array called ARR. So that's what we are doing here in this while loop. And yeah, that's done. That's how the merging function will work. And let's try to run it. Okay, I have to open the console. Okay, it's working perfectly fine. So for a given this 12, 11, 13, 5, 6, 7, 5, 6, 7, 11, 13, it's coming. Okay, so in a nutshell, if I have to summarize what merge sort is doing, using the sort function, we are dividing a problem into sub problems, and when the sub problem is once it gets to a unit sub problem where it cannot be divisible, we start trying to converge them. Converge them how? By comparing the each of the elements of the sub problem. So for that we'll create temporary variable arrays, that is L and R. From that we'll compare the elements of those arrays and put them finally them into ARR, that is the original array. So that's how the merge sort is happening. So divide the problem, and once it goes divisible, when you start converging them, you compare those sub problems and then you try to sort them. So this is one of the fastest algorithm that we can see. So in today's lecture, what we have seen is four implementations, basic implementation of four basic sorting arrays, that is bubble sort, insertion sort, selection sort, and merge sort. And one thing that you have to keep asking while you writing any algorithm, be it sort, search, or any other programming algorithm that you're going to write, is the perspectives from which you are looking at the problem. Here the sorting is quite simple to understand, but as from the implementation perspective or just by understanding perspective, but we generally overlook the different cases. What kind of cases would be there? That what if what if the case will like this, everything is sorted, then how much time will it take? What if the case arises that it is that the algorithm is too big and it is taking too much time, so can we find an alternative for that or not? Okay, so that's in a nutshell that you have to keep on asking from different lenses. Okay. Okay, so this one question, the exam is objective or theory? Mostly NPTEL exams are objective in nature. That means they will give you options, but you should have a grip of the theory to solve them. Okay, so that is one thing that you should keep on. Okay, I will stop the share. So it will be mostly the exam would be in the objective sense, but you should know the basically you should know the theory. Okay, I think you can turn on the microphone. I guess you can turn on. You can ask the question. Like Hema is raised her hand. So if you have any question, you can ask me right now. The session is over right now. We can ask. If you have any question, you can ask me now. Okay. So if that's the case, no questions, then so in today's thing, we have seen the implementation of sorting, multiple sort array, and we have seen that from how we can, in principle it's very easy to understand, but actually coding we have to see the multiple cases here, so we have to keep on looking from different perspective. Okay. Sir, exam conductor objective theory. Mostly, if I don't know per se exactly how it is going to set up, but mostly it is objective, if I remember very correctly. But they can change the thing. But you should know the theory aspect to give an answer for an objective question. I will provide the Java file. Yes, once this session is over, I will upload this in this channel. I have just posted that, and NPTEL also will give you these files as well. Okay, so Kavita, you have raised the hand. Can you please turn on your mic and say, or you can chat right in the chat also. Okay, thank you everyone. So we have two sessions remaining, so we will be looking for more different coding aspects uh, which we have to look and implement, because they might ask for some implementations as well, because it's basically a coding course, right? Only by looking at theory you might not, you have to keep on practicing the coding. You have to brush up your skills a lot, but keep on practicing. That's what I can say in a nutshell. Okay, Kavita, if you can write something quickly such that I should know if you have any doubt, such that otherwise I will close the session. I will stop the recording once.